the impossible discovery. The James Webb Space Telescope has just made a discovery that should be impossible. According to our current understanding of cosmology, nothing can be older than the Big Bang. The Big Bang marks the beginning of time itself, the moment when space, matter, and energy came into existence 13.8 billion years ago. Everything in the universe, from the smallest subatomic particle to the largest galaxy cluster, originated in that primordial explosion. Or, so we thought. Recent observations from JWST have revealed structures, galaxies, and phenomena that appear to predate the universe itself. These findings are sending shockwaves through the scientific community, forcing physicists and astronomers to question fundamental assumptions about cosmic history, the nature of time, and the very beginning of existence. The implications are staggering. If something truly exists that is older than the Big Bang, then either our understanding of the universe's age is wrong, or the Big Bang was not the absolute beginning we believed it to be. Perhaps time existed before the Big Bang. Perhaps our universe emerged from something even more ancient. Or perhaps the observations themselves reveal a flaw in our cosmological models that we've overlooked for decades. Whatever the explanation, the discovery represents one of the most significant challenges to modern cosmology since the theory of the Big Bang was first proposed. Before we dive into the details of what JWST found and what it means, drop it in the comments below where in the world you're watching from and what time it is there. Now, settle in as we explore a discovery that could rewrite everything we know about the origin of the universe. The James Webb Space Telescope. To understand the magnitude of this discovery, we first need to appreciate the incredible capabilities of the James Webb Space Telescope. JWST is not just an incremental improvement over previous space telescopes, it represents a quantum leap in our ability to observe the distant universe. Launched on the 25th of December 2021 and positioned at the second Lagrange point, about 1.5 million kilometers from Earth, JWST is the most powerful space telescope ever built. Its primary mirror spans 6.5 meters in diameter, more than twice the size of the Hubble Space Telescope's mirror, giving it nearly 7 times the light collecting area. But size is not JWST's only advantage. The telescope is optimized to observe in the infrared range of the electromagnetic spectrum, which is crucial for studying the early universe. When light travels across billions of light years of expanding space, it gets stretched by cosmic expansion, shifting visible light into the infrared. This means that light from the most distant, and therefore oldest, galaxies arrives at Earth as infrared radiation. Hubble, which observes primarily invisible and ultraviolet light, could only see so far back in time. JWST's infrared capabilities allow it to peer deeper into the cosmic past than any telescope before it, observing galaxies as they were just a few 100 million years after the Big Bang. The telescope's suite of 4 instruments works together to capture images and spectra of incredible detail. The Near-Infrared Camera, or NIRCam, serves as the telescope's primary imager, capturing stunning pictures of distant galaxies, star-forming regions, and exoplanets. The Near-Infrared Spectrograph, NIRSpec, can analyze the light from up to 100 objects simultaneously, breaking down their light into spectra that reveal their chemical composition, temperature, velocity, and distance. The Mid-Infrared Instrument, MIRI, observes at longer wavelengths, penetrating dust clouds and revealing processes invisible to shorter wavelength observations. And the Near-Infrared Imager and Slitless Spectrograph, NIRIS, specializes in studying exoplanet atmospheres and the earliest galaxies. Operating at temperatures just above absolute zero, cooled by a massive sunshield the size of a tennis court, JWST's instruments are extraordinarily sensitive. They can detect the faint infrared glow from objects so distant that their light has been traveling toward us for more than 13 billion years. This sensitivity has enabled JWST to observe galaxies that formed when the universe was less than 300 million years old, a period known as the cosmic dawn, when the first stars and galaxies began to illuminate the darkness. The telescope's observations are already revolutionizing our understanding of cosmic history. In its first year of operation alone, JWST has captured images of unprecedented clarity, revealing intricate details in distant galaxies, nebulae, and star-forming regions. It has detected the atmospheres of exoplanets, found some of the most distant galaxies ever observed, and provided new insights into the formation of stars and planets. But among all these groundbreaking discoveries, one stands out as particularly troubling for our standard cosmological model. JWST has found galaxies that appear too old, too massive, and too well developed to fit within our timeline of cosmic history. The standard model of cosmology, to understand why JWST's recent discoveries are so shocking, we need to review the standard model of cosmology, also known as the lambda CDM model. This model, built on decades of observations and theoretical work, describes the universe's evolution from the Big Bang to the present day. According to this framework, the universe began approximately 13.8 billion years ago in an incredibly hot, dense state. In the first fraction of a second, the universe underwent a period of exponential expansion called cosmic inflation, growing from quantum scales to macroscopic size faster than the speed of light. After inflation ended, the universe continued to expand and cool, but at a much slower rate. In the first few minutes after the Big Bang, nuclear reactions forged the lightest elements, hydrogen, helium, and traces of lithium. For the next 380,000 years, the universe was opaque, filled with a hot plasma of electrons and protons that scattered light in all directions. But as the temperature dropped below about 3000 degrees Kelvin, electrons and protons combined to form neutral hydrogen atoms, and light could finally travel freely. This moment, called recombination, released the cosmic microwave background radiation that we still observe today, a faint glow coming from every direction in the sky. After recombination came the cosmic dark ages, a period when the universe was filled with neutral hydrogen gas, but no stars had yet formed. Gravity slowly pulled matter together into denser and denser clumps, and eventually, after about 100 to 200 million years, the first stars ignited. These first stars, called population 3 stars, were massive, hot, and short-lived. They contained only hydrogen and helium, with no heavier elements, because no previous generations of stars had existed to create them. When these massive stars died in supernova explosions, they scattered the first heavy elements into space, enriching the gas from which subsequent generations of stars would form. Around the same time, the first small galaxies began to assemble. According to the lambda CDM model, structure formation proceeds hierarchically, with smaller objects forming first and gradually merging to create larger structures. Early galaxies were small, irregular, and actively forming stars. Over hundreds of millions of years, these proto-galaxies merged and grew, eventually forming the large spiral and elliptical galaxies we see in the nearby universe today. The timeline is crucial here. The first galaxies were not supposed to appear until at least 100 to 200 million years after the Big Bang, and they were expected to be small, dim, and relatively simple structures. The model makes specific predictions about what we should see when we look at very distant, and therefore very young, galaxies. We should see small, irregular systems with high rates of star formation, low metallicity, meaning few heavy elements, and relatively low masses. As we observe galaxies at progressively later times, we should see them growing larger and more massive, developing spiral arms or elliptical shapes, and forming stars at lower rates as they mature. This gradual assembly process is a cornerstone of modern cosmology, supported by decades of observations from telescopes like Hubble and ground-based observatories. Dark matter plays a crucial role in this picture. Although we cannot see dark matter directly, its gravitational influence shapes the distribution of ordinary matter throughout the universe. Computer simulations show that dark matter forms a cosmic web of filaments and nodes, and galaxies form where ordinary matter accumulates in the densest regions of this web. The rate at which structure grows depends on the properties of dark matter and the expansion rate of the universe, both of which are constrained by observations of the cosmic microwave background and the large-scale distribution of galaxies. Dark energy, which makes up about 68% of the universe's total energy content, also enters the picture. Dark energy causes the expansion of the universe to accelerate, and this acceleration affects when and how structures form. In the Standard Model, the interplay between gravity pulling matter together, the expansion of space pulling it apart, and the properties of dark matter and dark energy determines the timeline of cosmic history. Everything from the formation of the first stars to the assembly of galaxy clusters follows from this framework, and the predictions have been tested and confirmed by countless observations. Or at least, that's what we thought until JWST started sending back its data, the first shocking observations. When JWST began its science operations in the summer of 2022, astronomers were eager to see what it would reveal about the early universe. The telescope's first deep-field image, released in July 2022, showed thousands of galaxies in a tiny patch of sky, some of them among the most distant ever observed. The detail and clarity were breathtaking, far surpassing anything Hubble could achieve. But as astronomers began analyzing the data in detail, they noticed something strange. Some of the galaxies JWST was observing at very high redshifts, meaning very great distances and very early times, looked surprisingly mature. Redshift is a measure of how much the light from an object has been stretched by the expansion of space. The higher the redshift, the more distant the object and the earlier in cosmic history we're observing it. Hubble had previously found galaxies with redshifts around 10 or 11, corresponding to times when the universe was only 400 to 500 million years old. JWST, with its superior sensitivity, was expected to push this boundary back, finding galaxies at even higher redshifts, perhaps as high as 15 or 20, and it did. Within months, JWST had identified numerous candidate galaxies with redshifts between 10 and 20, corresponding to ages of 200 to 400 million years after the Big Bang. Some candidates even appeared to have redshifts above 20, suggesting they formed less than 200 million years after the Big Bang. Finding distant galaxies was not surprising. What was surprising was their appearance. According to the Standard Model, galaxies this young should be small, dim, and irregular. They should be in the early stages of assembly, with high rates of star formation as they rapidly build up their stellar population. Instead, many of the galaxies JWST observed were large, bright, and shockingly well organized. Some appeared to have masses equivalent to tens of billions of solar masses, comparable to the Milky Way today. They showed signs of having already formed large numbers of stars, with some even exhibiting features like spiral arms or disk structures that were not supposed to exist so early. One particularly striking example was a galaxy dubbed Sears 93316, initially reported to have a redshift around 16.7, which would place it just 250 million years after the Big Bang. The galaxy appeared mature and massive, with a stellar mass estimated at several billion times the mass of the Sunday. If confirmed, this would mean that somehow, in just 250 million years, gravity had assembled a structure containing billions of stars, each of which takes millions of years to form. The timescales simply did not add up. Subsequent analysis has called into question the exact redshift of this particular galaxy, and it may actually be closer and less extreme than initially thought, but it was just one of many troubling cases. Another galaxy, JWST 13, was confirmed to have a redshift of about 13.2, placing it around 300 million years after the Big Bang. It too appeared surprisingly bright and massive. Spectroscopic observations, which provide more reliable redshift measurements than photometry alone, began confirming that many of these early galaxies were indeed at the extreme distances suggested by their colors. With each confirmation, the tension with the standard model grew. How could such massive, mature galaxies exist so early in cosmic history? Astronomers started calling this the impossibly early galaxy problem. The term was not meant to suggest that the galaxies were literally impossible, but rather that their existence challenged key assumptions in our cosmological models. If galaxies this large and mature could form in just a few 100 million years, then either star formation and galaxy assembly proceeded much more efficiently in the early universe than we thought, or something fundamental about our timeline was wrong. Some researchers began whispering about more radical possibilities. What if the universe was older than we thought? What if the Big Bang was not the beginning? What if there were structures that predated the Big Bang itself? Analyzing the data, as the initial shock of these observations wore off, astronomers began the painstaking work of analyzing the data in detail, trying to determine whether the early galaxies were truly as massive and mature as they appeared, or whether there were alternative explanations. One possibility was that the measurements were simply wrong. Determining the distance to a galaxy based on its colors and spectrum is not always straightforward, especially for very distant objects where the light is extremely faint and can be contaminated by foreground sources or instrumental artifacts. Photometric redshifts, which estimate distance based on the colors of a galaxy as measured through different filters, are less reliable than spectroscopic redshifts, which are based on identifying specific spectral lines in the galaxy's light and measuring their wavelength shift. Many of the initial JWST detections relied on photometric redshifts, which can sometimes be fooled by unusual stellar populations or dust. For example, an older, dusty galaxy at a moderate distance might have colors similar to a young, dust-free galaxy at a very high redshift, leading to confusion. Spectroscopic follow-up observations were crucial for confirming the distances to these galaxies. JWST's NIRSpec instrument has the capability to obtain spectra of many galaxies simultaneously, and teams of astronomers quickly proposed and executed observations to confirm the redshifts of the most intriguing candidates. In many cases, the spectroscopic redshifts confirmed that the galaxies were indeed at the extreme distances suggested by their colors. In other cases, the galaxies turned out to be closer than initially thought, resolving the apparent conflict with the standard model. But even accounting for these revisions, a significant number of genuine high redshift, massive galaxies remained, posing a real challenge to our understanding. Another complication was estimating the masses of these galaxies. The mass of a galaxy is typically inferred from its luminosity, based on models of how much light stars of different types emit. If a galaxy contains old, evolved stars, it might be quite massive, even if it does not appear extremely bright. Conversely, if it contains mainly young, hot stars, it could be quite bright, but not as massive as it appears. Dust can also complicate matters, absorbing and scattering starlight in ways that affect both the observed brightness and the inferred mass. Some researchers suggested that the early galaxies might be less massive than initial estimates, once all these factors were properly accounted for. However, even with conservative estimates, many of the early galaxies still appeared to be more massive than the standard model comfortably allowed. Computer simulations of galaxy formation, which track how dark matter and ordinary matter evolve from the initial conditions of the Big Bang, struggle to produce such massive galaxies so early. The simulations show that structure formation is a gradual process, with the first galaxies being small and only slowly growing through mergers and continued star formation. To match the JWST observations, the simulations need to be tweaked, either by increasing the efficiency of star formation, by allowing for earlier start times for structure formation, or by modifying other parameters in ways that might have broader implications for cosmology. Some astronomers propose that the early universe might have been more conducive to rapid star formation than previously thought. Perhaps the first stars formed more quickly, or perhaps they were more efficient at converting gas into stars, leaving less gas unconverted. Others suggested that the initial seeds of galaxies, the small fluctuations in density present in the early universe, might have been slightly larger or more numerous than our models assumed. If so, structure could have started forming earlier and progressed faster. These modifications, while possible, raised new questions about why the early universe would behave so differently from later epochs. A more radical possibility, which some researchers began to consider seriously, was that the standard cosmological timeline was wrong. What if the universe was not 13.8 billion years old, but somewhat older? An older universe would allow more time for galaxies to form and mature, potentially explaining the observations. But this idea immediately ran into problems. The age of the universe is not an arbitrary parameter. It is constrained by multiple independent lines of evidence, including observations of the cosmic microwave background, measurements of the expansion rate, studies of the oldest stars, and calculations of Big Bang nucleosynthesis. All of these point consistently to an age around 13.8 billion years. Changing this number would require revising not just one measurement, but an entire interlocking framework of observations and theory. The crisis in cosmology. The term crisis in cosmology began appearing in scientific papers and popular articles as the implications of the JWST observations sank in. The crisis was not just about a few unexpectedly massive galaxies. It was about the possibility that our entire cosmological framework, the lambda CDM model that had been so successful for decades, might need significant revision. The situation was reminiscent of earlier crises in physics, moments when observations could not be reconciled with prevailing theory and a revolution was needed. One of the most famous such crises occurred in the late 19th century when physicists struggled to explain the spectrum of blackbody radiation. Classical physics predicted that hot objects should emit infinite amounts of ultraviolet light, a result known as the ultraviolet catastrophe. The resolution came from Max Planck's introduction of the quantum hypothesis, the idea that energy is emitted in discrete chunks rather than continuously. This radical idea eventually led to the development of quantum mechanics, revolutionizing physics. Could JWST's observations represent a similar moment where nature is telling us that our current theories are incomplete? There were precedents in cosmology itself. In the 1920 seconds, observations by Edwin Hubble showed that the universe was expanding, overturning the previously held belief in a static cosmos. In the 1960 seconds, the discovery of the cosmic microwave background provided strong evidence for the Big Bang theory, eliminating competing models like the steady-state universe. In the late 1990 seconds, observations of distant supernovae revealed that the universe's expansion was accelerating, leading to the discovery of dark energy. Each of these discoveries forced a re-evaluation of fundamental assumptions and led to new paradigms. Perhaps JWST's findings heralded another such shift. Some cosmologists began proposing alternative models to explain the observations. One class of models suggested modifications to the nature of dark matter. If dark matter interacted more strongly than we thought, or if it had different properties in the early universe, it might accelerate structure formation, allowing galaxies to assemble faster. Another class of models focused on dark energy, proposing that its properties might have been different in the early universe, affecting the expansion rate and the timeline of structure formation. More radically, some researchers questioned whether the Big Bang itself was truly the beginning. In standard cosmology, The Big Bang is a singularity, a point where density and temperature were infinite, and the laws of physics, as we know them, break down. General relativity predicts this singularity, but it is widely believed that a complete theory of quantum gravity would replace the singularity with something more physical. Perhaps the Big Bang was not a beginning, but a transition, a bounce from a previous contracting phase, or an emergence from a more fundamental, pre-existing state. If so, then structures or patterns from before the Big Bang might have influenced the formation of galaxies afterward, potentially explaining why some galaxies appear older than expected. Cyclic cosmologies, in which the universe undergoes repeated cycles of expansion and contraction, have been proposed by various theorists over the years. In these models, the Big Bang is just one event in an infinite series, and information or structure from previous cycles might persist in some form. String theory also allows for scenarios where our universe is a brane in a higher dimensional space, and interactions with other branes or structures in the bulk could affect cosmic history in ways not accounted for in standard models. These ideas are speculative, but the JWST observations were prompting some cosmologists to take them more seriously. Another possibility was that the Hubble constant, the current expansion rate of the universe, might be different from what we thought. There has been an ongoing tension in cosmology between measurements of the Hubble constant from the cosmic microwave background and measurements from nearby supernovae and other distance indicators. The two methods give values that differ by several percent, more than can be explained by measurement uncertainties. If the higher value from local measurements is correct, it might imply a younger age for the universe and a faster expansion, which could affect the timeline of structure formation. However, resolving this tension in a way that also explains the early massive galaxies is not straightforward. Some physicists even began to question whether the speed of light or other fundamental constants might have been different in the early universe. If physical constants were variable, many of our assumptions about cosmic history would need to be revisited. This idea, known as variable speed of light cosmology, has been proposed before to address other cosmological puzzles, but it remains highly controversial and lacks strong empirical support. Still, the JWST observations were forcing the community to consider ideas that might once have seemed too speculative. But before we continue exploring these radical possibilities, I want to thank today's sponsor, Audible. Understanding the complexities of cosmology and the discoveries being made by JWST requires diving deep into the science, and there's no better way to learn than by listening to audiobooks from experts in the field. Audible offers an incredible selection of science books, from classics like A Brief History of Time by Stephen Hawking, to cutting-edge explorations of cosmology, quantum mechanics, and astrophysics. Whether you're commuting, exercising, or just relaxing, Audible lets you turn any moment into a learning opportunity. I've been listening to books about the early universe and the latest findings from JWST, and it's been fascinating. Plus, Audible members get access to exclusive sales and discounts, as well as a selection of Audible originals. Right now, you can try Audible free for 30 days. Just visit audible.com/spacedust or text spacedust to 500 to get started. That's audible.com/spacedust or text spacedust to 500 for your free trial. Now, let's get back to the mystery of what JWST might have discovered. What if the universe is older? One of the most straightforward ways to resolve the tension between JWST's observations and the standard model would be if the universe was simply older than we think. If the Big Bang occurred not 13.8 billion years ago, but say 15 or 16 or even 20 billion years ago, then there would be more time for galaxies to form and mature, and the early massive galaxies would not be as surprising. But changing the age of the universe is not a simple matter. The 13.8 billion year age is not based on a single measurement, but emerges from a comprehensive set of interlocking observations and calculations. The age of the universe is calculated from the expansion rate measured by the Hubble constant and the history of that expansion, which depends on the composition of the universe in terms of matter, and dark energy. The cosmic microwave background provides a snapshot of the universe at 380,000 years old, and the patterns in the CMB allow us to infer the expansion history and thus the total age. The measurements from the Planck satellite, which mapped the CMB in exquisite detail, give an age of 13.797 billion years, with an uncertainty of only about 20 million years. This is remarkably precise. Independent checks come from the ages of the oldest stars. Globular clusters, dense collections of ancient stars found in the halos of galaxies, contain stars that are among the oldest in the universe. By studying the properties of these stars and comparing them to models of stellar evolution, astronomers can estimate their ages. The oldest globular cluster stars appear to be around 12 to 13 billion years old, consistent with a universe age of 13.8 billion years. If the universe was significantly older, we would expect to find stars that are also older, but we do not. Big Bang nucleosynthesis provides another constraint. In the first few minutes after the Big Bang, nuclear reactions produced helium, deuterium, and lithium in specific ratios that depend on the density of ordinary matter and the expansion rate. Observations of the abundances of these elements in the universe today match the predictions of nucleosynthesis for a universe with the standard age and composition. Changing the age of the universe would alter these predictions, potentially bringing them into conflict with observations. The expansion history of the universe can also be traced using observations of distant supernovae, which serve as standard candles. By measuring how the brightness of supernovae changes with redshift, astronomers can map out how the universe has expanded over time. These observations led to the discovery of dark energy in 1998 and are consistent with the standard age of 13.8 billion years. If the universe were older, the supernova data would need to be reinterpreted, which would have implications for our understanding of dark energy. Given all these interlocking constraints, simply asserting that the universe is older is not viable without a comprehensive revision of many aspects of cosmology. Some researchers have tried to explore whether specific modifications to the standard model could accommodate an older age while still fitting the other data. For example, if dark energy behaved differently in the past, it might alter the expansion history in ways that could increase the age. But such modifications need to be carefully tested against all available observations, and so far, no one has found a version that works smoothly. Another approach is to question whether the speed of light or other fundamental constants were different in the early universe. If light traveled faster in the past, then the relationship between distance, time, and the expansion of the universe would be altered, potentially allowing for an older age. However, changing fundamental constants introduces a host of new problems and requires new physics that we do not currently have evidence for. Most physicists are reluctant to go down this path unless absolutely necessary. There is also the possibility that our measurements of the Hubble constant are wrong. As mentioned earlier, there is a tension between different methods of measuring the expansion rate. If the lower value from the CMB is correct, the universe is slightly older. If the higher value from local measurements is correct, it is slightly younger. But the difference is only a few 100 million years, not enough to explain galaxies that appear to need several billion years to form. Resolving the Hubble tension might help, but it is unlikely to solve the early galaxy problem on its own. Alternatives to the Big Bang: if the universe is not older than we think, then perhaps the Big Bang itself was not the absolute beginning. This idea, once relegated to the fringes of cosmology, is gaining renewed attention in light of JWST's observations. There are several ways in which the Big Bang might not be the ultimate origin of everything, and each has different implications for what might have existed before and how it might have influenced what came after. One possibility is the cyclic or oscillating universe model. In this scenario, the universe undergoes repeated cycles of expansion and contraction. Each cycle begins with a big bang, expands for billions of years, then eventually recollapses in a big crunch, only to bounce back in a new big bang. This process might repeat infinitely, with each cycle being one phase in an eternal cosmic rhythm. The appeal of this model is that it avoids the problem of an absolute beginning, which many find philosophically troubling. If the universe has always existed, cycling through phases of expansion and contraction, then there is no need to explain how it came from nothing. In cyclic models, information or structure from previous cycles might carry over into the next cycle. Perhaps the seeds of galaxies, imprinted as density fluctuations in one cycle, persist through the bounce and reappear in the next cycle, giving structure formation a head start. This could explain why JWST sees galaxies that appear older than expected. They are not really older than the current Big Bang, but they are built on foundations laid in a previous cycle. However, cyclic cosmologies face significant challenges. One is the problem of entropy. The second law of thermodynamics states that entropy, or disorder, always increases. In a cyclic universe, entropy would build up over each cycle, and eventually the universe would reach a state of maximum entropy where no further cycles could occur. Some cyclic models try to address this by proposing mechanisms that reset entropy during the bounce, but these mechanisms are not well understood. Another model is the ekpyrotic scenario, inspired by string theory. In this model, our universe is a three-dimensional brain embedded in a higher dimensional space, and the Big Bang was the result of a collision between our brain and another brain. Before the collision, both brains existed independently, possibly for an indefinite time. The collision released enormous energy, which we perceive as the Big Bang, but the brains themselves might be much older. Structures, or fields on the brains, before the collision could influence the initial conditions of our universe, potentially affecting galaxy formation. The ekpyrotic model makes predictions about the patterns of fluctuations in the cosmic microwave background, and so far, observations are consistent with it, though they do not provide definitive proof. Eternal inflation, which we discussed in the previous video about what lies beyond the universe, also offers a way in which the Big Bang might not be the ultimate beginning. In eternal inflation, a vast inflating region gives birth to countless bubble universes, each with its own Big Bang. The inflating region itself might have existed indefinitely into the past, or it might have emerged from some prior state. If our Big Bang was just one bubble nucleating within eternal inflation, then the broader inflating space is older than our universe, and the processes occurring in that space might affect the properties of newly formed bubbles. Some researchers have speculated that interactions between bubbles, or inheritance of structure from the inflating background, could lead to anomalies in the early universe that might show up as unexpectedly mature galaxies. Quantum cosmology offers yet another perspective. In this framework, the universe emerged from a quantum state, possibly a quantum fluctuation in a pre-existing quantum vacuum. The concept of before the Big Bang might not even make sense in a conventional way, because time itself is a quantum variable that only becomes well-defined after the universe reaches a certain size. However, the quantum state from which the universe emerged could have structure or properties that influence the subsequent evolution, and this might affect how quickly galaxies form. These ideas are highly speculative and difficult to test, but they illustrate the range of possibilities that cosmologists are considering. String theory provides a rich landscape of possible cosmologies. In some string theory scenarios, there are multiple spatial dimensions beyond the three we experience, and our universe might be just one slice or brain in this higher dimensional space. The extra dimensions could contain energy, fields, or even other universes, and interactions with these structures could affect the evolution of our universe in ways not captured by the standard model. Some string theorists have proposed that the Big Bang was a transition from a pre-Big Bang phase governed by different physics, and that relics or echoes from that phase might be detectable in the early universe. All of these alternatives to the standard Big Bang picture are speculative, and none has been definitively proven. But the JWST observations are forcing cosmologists to take them more seriously. If the standard model cannot comfortably accommodate the early massive galaxies, then perhaps it is time to explore models where the Big Bang is not the absolute beginning. These explorations are in their early stages, and it remains to be seen whether any of them can provide a consistent framework that matches all observations. But the willingness to question foundational assumptions is a sign of a healthy and vibrant scientific field, and it is precisely this kind of questioning that has led to breakthroughs in the past. Could there be pre-Big Bang structures? One of the most tantalizing possibilities raised by JWST's observations is that some structures in the universe might have originated before the Big Bang. This idea sounds paradoxical at first. How can something exist before the beginning of time? But as we have seen, the Big Bang might not be the absolute beginning. If there was a pre-Big Bang phase, whether a previous cycle, a quantum state, or a different cosmic epoch, then structures or patterns from that phase might have left imprints on our universe. In cyclic cosmologies, the transition from one cycle to the next is a critical phase. If the universe contracts to a very small size before bouncing, quantum effects become important, and the classical description of space-time breaks down. A complete theory of quantum gravity would be needed to describe what happens at the bounce, and such a theory does not yet exist. However, some models suggest that during the bounce, information is preserved in a way that allows density fluctuations or other features from the previous cycle to carry over into the new cycle. These seed fluctuations could then serve as the starting points for structure formation, giving galaxies a head start. In the ekpyrotic scenario, the pre-collision brains might have had their own structures, such as variations in energy density or configurations of fields. When the brains collided, these structures would be imprinted on the hot, dense state that became our universe. As the universe expanded and cooled, these imprints would evolve into the density fluctuations that seeded galaxies. If the pre-collision brains were older or more evolved than the age of our universe would suggest, then the galaxies that formed might appear anomalously mature. Eternal inflation offers another route to pre-Big Bang structure. In this framework, the inflating region that gave birth to our bubble universe might have had variations in its properties, such as fluctuations in the inflaton field, the field driving inflation. These fluctuations could be inherited by the bubble, affecting the initial conditions for structure formation. Moreover, if our bubble collided with another bubble, the collision could leave a distinctive signature, perhaps enhancing structure formation in certain regions and leading to the early appearance of massive galaxies. Some cosmologists have speculated about even more exotic possibilities. For example, if there are extra dimensions, structures in those dimensions might cast shadows or have effects on our three-dimensional universe. These effects could manifest as anomalies in the distribution or properties of galaxies. Alternatively, if our universe is part of a multiverse, quantum entanglement or other connections between different universes might allow information to leak from one universe to another, influencing the evolution of galaxies in ways we do not yet understand. Testing these ideas is extremely challenging. Most of them make predictions that are either very subtle or very difficult to distinguish from alternative explanations. However, JWST's detailed observations of the early universe provide a new testing ground. By measuring the masses, star formation rates, chemical compositions, and morphologies of early galaxies, astronomers can compare the data to predictions from different models. If a particular model consistently does a better job of matching the observations, it gains credibility. Conversely, If all models struggle to fit the data, it might indicate that we need even more radical ideas. One promising avenue is to look for statistical patterns in the distribution of early galaxies. If pre-Big Bang structures influence galaxy formation, there might be correlations or anomalies that differ from what the standard model predicts. For example, if certain regions of the sky have an unusually high density of early massive galaxies, it might indicate a localized enhancement due to pre-Big Bang effects. Similarly, if the orientations of galaxies show unexpected alignments, it could hint at large-scale structure inherited from a previous phase. Another approach is to search for relics of pre-Big Bang physics in the cosmic microwave background. While the CMB is primarily a snapshot of the universe at 380,000 years old, it might contain subtle imprints from earlier epochs, including the pre-Big Bang phase. Anomalies such as the cold spot, a surprisingly large cool region in the CMB, have been debated for years, with some researchers suggesting they might be due to exotic effects like bubble collisions or topological defects. Improving measurements of the CMB and developing more sophisticated analysis techniques might reveal additional clues. The possibility of pre-Big Bang structures is still highly speculative, and most cosmologists remain skeptical. The standard Big Bang model has been extraordinarily successful, and overturning it would require overwhelming evidence. However, the JWST observations are at least raising the question, and in science, asking the right questions is often the first step toward new discoveries. Whether or not structures older than the Big Bang truly exist, the search for them is pushing the boundaries of our understanding and leading to new insights into the nature of time, space, and the origin of the cosmos, the role of dark matter and dark energy. Any explanation for the early massive galaxies observed by JWST must account for the roles of dark matter and dark energy, the two dominant components of the universe's mass energy content. Dark matter provides the gravitational scaffolding for structure formation, while dark energy drives the accelerated expansion that affects the growth of structures. If either of these components behaved differently in the early universe than we currently assume, it could have profound implications for galaxy formation. Dark matter is essential for galaxy formation because ordinary matter alone cannot clump together fast enough to form galaxies in the time available. Photons and ordinary matter were tightly coupled in the early universe, and this coupling resisted gravitational collapse. Dark matter, which does not interact with photons, could begin clumping earlier, creating potential wells into which ordinary matter could fall once the universe became transparent. This head start is crucial for explaining how galaxies formed as early as they did. However, the standard model assumes that dark matter is cold, meaning it moves slowly compared to the speed of light, and that it is collisionless, meaning dark matter particles do not interact with each other or with ordinary matter, except through gravity. If dark matter were warmer, moving at higher velocities, it would smooth out small-scale structures, potentially delaying galaxy formation. Conversely, if dark matter particles interacted with each other even weakly, through a process called self-interaction, it could affect how dark matter clumps and how quickly galaxies form. Some researchers are exploring whether modifications to the properties of dark matter could explain the JWST observations. One possibility is that dark matter in the early universe was colder or clumpier than we thought, allowing structures to form even faster. Another is that there might be multiple types of dark matter with different properties, and that one type dominated in the early universe while another dominates today. These ideas are speculative but testable. If different dark matter physics were at play in the early universe, it might leave signatures not only in galaxy formation, but also in the cosmic microwave background and in the distribution of dark matter in galaxies today. Dark energy, on the other hand, primarily affects the universe on the largest scales and at late times. In the Standard Model, dark energy is a cosmological constant, a form of energy with constant density that causes the expansion of the universe to accelerate. This acceleration began relatively recently, around 5 billion years ago, and has been growing ever since. Before that, the universe's expansion was decelerating, slowed by the gravitational attraction of matter. However, some models propose that dark energy might not be a cosmological constant, but a dynamical field called quintessence, whose energy density changes over time. If dark energy were stronger or had different properties in the early universe, it could have affected the expansion rate and the timeline of structure formation. For example, if dark energy were weaker in the early universe, the expansion would have been slower, giving gravity more time to pull matter together and potentially accelerating galaxy formation. Alternatively, if dark energy was stronger in the early universe before decreasing to its current value, it might have affected the initial conditions for structure formation. Some models propose that dark energy and dark matter might be coupled, with interactions between them affecting how structures grow. If such interactions were stronger in the early universe, they could have enhanced structure formation in ways not captured by the Standard Model. Another exotic possibility is that dark energy and dark matter are both manifestations of a more fundamental field or phenomenon that we do not yet understand. Some theories propose a unified dark sector, where dark matter and dark energy arise from different aspects of the same underlying physics. If this is true, the behavior of both components in the early universe might differ from what we assume, and these differences could affect galaxy formation in complex ways. Testing these ideas requires comparing detailed models against observations. JWST's data on early galaxies provides crucial constraints, but other observations are also important. Measurements of the cosmic microwave background, the large-scale distribution of galaxies, the clustering of dark matter inferred from gravitational lensing, and the expansion history traced by supernovae all contribute to our understanding of dark matter and dark energy. By combining all these data, cosmologists can test whether modifications to the standard picture of dark matter and dark energy can explain the early massive galaxies without coming into conflict with other observations. The Hubble tension. One of the most significant ongoing puzzles in cosmology is the Hubble tension, a discrepancy between different measurements of the universe's current expansion rate. This tension has been growing for years, and it might be related to the issues raised by JWST's observations of early galaxies. Understanding the Hubble tension is important for assessing whether our cosmological model is fundamentally correct or whether it needs revision. The Hubble constant, usually denoted h0, quantifies how fast the universe is expanding today. It is measured in kilometers per second per megaparsec, meaning that for every megaparsec, about 3.26 million light-years of distance, galaxies are receding at a certain speed. The value of h0 determines the age of the universe, the scale of cosmic structures, and the timeline of cosmic history. Two main methods are used to measure h0, and they give results that disagree by about 9%, which is far more than can be explained by measurement uncertainties. The first method uses the cosmic microwave background. By measuring the patterns of fluctuations in the CMB, cosmologists can infer the properties of the early universe, including the expansion rate. Using this information and the Standard Model of cosmology, they can extrapolate forward to calculate the current expansion rate. The Planck satellite, which made the most precise CMB measurements to date, gives a value of h0 around 67 kilometers per second per megaparsec. This method has small uncertainties, and the result is consistent with earlier CMB measurements from WMAP and other experiments. The second method uses observations of relatively nearby objects, such as Cepheid variable stars and Type Ia supernovae, which serve as distance indicators. By measuring the distances and velocities of these objects, astronomers can directly measure the expansion rate in the local universe. This method, pioneered by teams led by Adam Rees and others, gives a value of H0 around 73 km per second per megaparsec, significantly higher than the CMB result. This discrepancy, around 9%, is highly significant statistically, and has persisted despite efforts to refine both measurements. The Hubble tension suggests that either one of the measurements is wrong, or the standard model of cosmology is incomplete. If the local measurement is correct, the universe is expanding faster today than the CMB predicts, which might indicate new physics, such as a form of dark energy that has changed over time, or additional relativistic particles in the early universe that affected the expansion rate. If the CMB measurement is correct, then there might be systematic errors in the local distance measurements, though this seems increasingly unlikely given the care with which those measurements have been made. One intriguing possibility is that the Hubble tension is related to the early massive galaxies observed by JWST. If the universe's expansion history were different from what we assume, it could affect both the age of the universe and the timeline of structure formation. For example, if the expansion were faster in the early universe, it might delay structure formation, making it harder to form massive galaxies quickly. Conversely, if the expansion was slower, it might accelerate structure formation. But this would conflict with CMB measurements. Finding a consistent picture that resolves both the Hubble tension and the early galaxy problem is a major challenge. Some cosmologists have proposed that the solution to the Hubble tension might involve modifications to the standard model, such as varying fundamental constants, additional fields or particles, or changes to the behavior of dark energy or dark matter. If any of these modifications also help explain the early massive galaxies, it would be a powerful argument in favor of the new physics. However, so far, no single proposal has successfully addressed both issues while remaining consistent with all other observations. Another possibility is that the Hubble tension and the early galaxy problem are unrelated, and that each requires its own explanation. This would be less elegant, but might be closer to the truth. Science does not always provide tidy, unified answers, and sometimes different puzzles have different solutions. Nevertheless, the fact that both issues involve the timeline and evolution of the universe suggests that they might be connected, and many researchers are actively exploring this possibility. Rethinking star formation. One of the key questions raised by JWST's observations is whether our understanding of star formation in the early universe is correct. Stars are the building blocks of galaxies, and the rate at which they form determines how quickly galaxies can grow in mass. If star formation was more efficient in the early universe than we thought, it might explain how galaxies became so massive so quickly. In the standard picture, star formation occurs when clouds of gas collapse under their own gravity. As the gas becomes denser, it heats up, and eventually the core becomes hot enough for nuclear fusion to ignite, giving birth to a star. The efficiency of this process depends on many factors, including the temperature and density of the gas, the presence of heavy elements that can cool the gas and allow it to collapse more easily, and the influence of feedback from previous generations of stars, such as supernova explosions and stellar winds that can heat the gas and prevent further collapse. In the early universe, conditions were different from today. The gas was almost entirely hydrogen and helium, with only trace amounts of heavier elements. This low metallicity means that the gas could not cool as efficiently as gas today, which contains carbon, oxygen, and other elements that radiate energy effectively. As a result, the first stars, called population 3 stars, are thought to have been very massive, perhaps hundreds of times the mass of the Sunday. These massive stars burn through their fuel quickly, living only a few million years before exploding as supernovae. The supernovae from population The stars enriched the surrounding gas with heavy elements, making subsequent generations of stars, called population 2 and population 1 stars, more like the stars we see today. The transition from population 3 to population 2 star formation is a critical phase in cosmic history, and our understanding of this transition is based on theoretical models and computer simulations. Since we have not yet directly observed population 3 stars, JWST's observations suggest that star formation in the early universe might have been even more vigorous than we thought. Some of the early galaxies show evidence of forming stars at rates of hundreds or even thousands of solar masses per year, far higher than typical rates in galaxies today. If these rates are sustained for even a few 100 million years, they could build up stellar masses of tens of billions of solar masses, comparable to the Milky Way. But sustaining such high star formation rates requires a continuous supply of gas, and it also raises questions about why star formation was so efficient. One possibility is that the initial mass function, the distribution of stellar masses at birth, was different in the early universe. If more low-mass stars formed relative to high-mass stars, then a given amount of gas could produce more total stellar mass. Low-mass stars also live much longer than high-mass stars, so they would contribute to the galaxy's mass for billions of years. However, changing the initial mass function has other implications, such as affecting the chemical enrichment and the light output of galaxies, and these need to be checked against observations. Another factor is feedback. Massive stars and supernovae release enormous amounts of energy, which can heat the surrounding gas and drive winds that blow gas out of the galaxy. This negative feedback can suppress star formation, limiting how fast galaxies can grow. In the Standard Model, feedback is thought to be important in regulating star formation and preventing all the gas from turning into stars too quickly. However, if feedback were less effective in the early universe, perhaps because the gas was less dense or because magnetic fields were weaker, then star formation could proceed more efficiently. Some researchers have proposed that the early universe might have had regions of unusually high gas density or low turbulence, creating conditions that favored rapid star formation. Others have suggested that the first galaxies might have experienced bursts of star formation triggered by mergers or by the infall of cold gas streams from the cosmic web. These bursts could temporarily push star formation rates to very high values, allowing galaxies to accumulate mass quickly. JWST's spectroscopic capabilities are allowing astronomers to study the properties of early galaxies in detail, including their star formation rates, metallicities, and the presence of emission lines that indicate active star formation. By comparing these observations to models, researchers can test whether standard assumptions about star formation hold in the early universe or whether modifications are needed. Early results suggest that star formation might indeed have been more efficient, but more data is needed to draw firm conclusion. Could primordial black holes explain the observations? An intriguing and somewhat speculative idea is that primordial black holes might play a role in the early massive galaxies observed by JWST. Primordial black holes are hypothetical black holes that formed in the very early universe, not from collapsing stars, but from density fluctuations in the hot, dense plasma shortly after the Big Bang. If such black holes exist, they could have influenced galaxy formation in interesting ways. In the standard picture, supermassive black holes, with masses of millions to billions of times the Sun, reside at the centers of most galaxies, including our own Milky Way. These black holes are thought to have grown over cosmic time through the accretion of gas and through mergers with other black holes. However, JWST has observed some galaxies at very high redshifts that appear to host supermassive black holes already, when the universe was less than 1 billion years old. Growing such massive black holes so quickly is challenging within the Standard Model, and it has led to renewed interest in alternative formation mechanisms, including primordial black holes. If primordial black holes, with masses of thousands or even millions of solar masses formed in the early universe, they could serve as seeds for the supermassive black holes we see today. These seed black holes could begin accreting gas immediately, growing rapidly, and providing the nuclei around which galaxies assemble. Moreover, the gravitational pull of primordial black holes could help pull ordinary matter together, accelerating the formation of galaxies. If there were many primordial black holes scattered throughout the early universe, they could act as catalysts for structure formation, helping to explain the early appearance of massive galaxies. Primordial black holes could also contribute to the dark matter in the universe. If they formed in sufficient numbers and with the right mass range, they could account for some or all of the missing mass that we attribute to dark matter. This would be an elegant solution, avoiding the need for new exotic particles. However, observations place strong constraints on the abundance of primordial black holes. Gravitational lensing, the disruption of binary stars, and the effects on the cosmic microwave background all limit how many primordial black holes can exist at various mass scales. Current constraints suggest that primordial black holes cannot account for all of dark matter, but they might make up a fraction. Another way primordial black holes could affect early galaxies is through their influence on star formation. When a black hole accretes gas, it releases energy in the form of radiation and jets. This energy can heat the surrounding gas, either suppressing star formation through negative feedback or, in some cases, triggering star formation by compressing the gas. The interplay between black hole growth and star formation is complex, and simulations are only beginning to explore how it might play out in the early universe. JWST's observations of active galactic nuclei, the luminous regions around accreting supermassive black holes, in high redshift galaxies are providing new insights into how black holes and galaxies co-evolve. Some early galaxies show signatures of powerful AGN, indicating that their central black holes were already growing rapidly. If some of these black holes originated as primordial black holes, it might help explain their early appearance. However, distinguishing between black holes that grew from stellar remnants and those that formed primordially is difficult, and more observations are needed. The idea that primordial black holes might explain JWST's observations is speculative and faces significant challenges. Forming primordial black holes requires specific conditions in the early universe, such as large density fluctuations, and such conditions might leave other signatures that we have not yet seen. Moreover, even if primordial black holes exist, it is not clear that they would be distributed in a way that consistently produces the patterns of early galaxy formation that JWST observes. Nevertheless, the hypothesis is worth exploring, and it adds another layer to the rich tapestry of ideas being considered to explain the data. The role of reionization. The epoch of reionization is another critical phase in cosmic history that might be relevant to the early massive galaxies observed by JWST. Reionization refers to the process by which neutral hydrogen gas in the universe was ionized, or stripped of its electrons, by the ultraviolet light from the first stars and galaxies. This process transformed the universe from opaque to transparent, allowing light to travel freely over large distances. Before reionization, the universe was filled with neutral hydrogen that absorbed ultraviolet light. This meant that UV photons from the first stars could not travel far before being absorbed, and the universe was essentially fogged in. As more stars formed and emitted more UV radiation, bubbles of ionized gas began to grow around the first galaxies. Eventually, these bubbles overlapped, and the entire universe became ionized. This process is thought to have occurred between about 150 million and 1 billion years after the Big Bang, though the exact timeline is uncertain. JWST is uniquely positioned to study the epoch of reionization because it can observe galaxies during this period and measure their UV output. By studying the spectra of these galaxies, astronomers can determine how much ionizing radiation they are producing and how far that radiation can travel before being absorbed. Early results suggest that the first galaxies might have been more efficient at ionizing their surroundings than previously thought, producing more UV photons per unit of star formation. The efficiency of reionization depends on several factors, including the number of stars being formed, the fraction of UV photons that escape from galaxies rather than being absorbed by dust or gas within the galaxy, and the clumpiness of the intergalactic medium. If galaxies were more effective at ionizing the universe, it might indicate that they were forming stars more vigorously, or that their structure allowed more radiation to escape. This could be related to why some early galaxies appear so massive. Reionization also affects the growth of galaxies. Once the universe is ionized, the gas in the intergalactic medium is heated, making it harder for small galaxies to accrete gas and form stars. This suppression of star formation in small galaxies, sometimes called UV feedback or reionization feedback, might influence the distribution of galaxy masses. If reionization occurred earlier or more rapidly than expected, it could alter the timeline of galaxy formation and affect which galaxies grow large and which do not. JWST's observations of the reionization epoch are providing crucial data for understanding this process. By measuring the ionization state of the gas around early galaxies and studying how the ionized fraction changes with time, astronomers can reconstruct the history of reionization and test models of how it proceeds. If the observations show that reionization was driven by galaxies that were more massive or more numerous than expected, it would support the idea that galaxy formation in the early universe was unusually efficient. There is also the possibility that reionization was not uniform across the universe. Different regions might have been ionized at different times depending on the local density of galaxies and the efficiency of ionizing radiation. If some regions were ionized earlier, it might create conditions that favored more rapid galaxy growth in those regions, leading to a patchwork of environments with varying rates of structure formation. JWST's wide-field surveys are beginning to map out the spatial distribution of early galaxies, and this data will help test whether reionization was indeed patchy, and whether this patchiness is linked to the observed variation in galaxy properties, alternative explanations, and systematics. As the debate over JWST's early galaxy observations continues, it is important to consider alternative explanations that do not require radical changes to cosmology. Science progresses by rigorously testing hypotheses and ruling out mundane explanations before accepting extraordinary ones. In the case of the early massive galaxies, there are several potential alternative explanations related to observational systematics, data interpretation, and the limitations of our measurements. One possibility is that some of the galaxies are not as distant as they appear. Photometric redshifts, which estimate distance based on the colors of galaxies, can sometimes be incorrect, especially for galaxies with unusual stellar populations or dust content. A dusty galaxy at a lower redshift might have colors similar to a young galaxy at a higher redshift, leading to a misidentification. Spectroscopic follow-up is crucial for confirming redshifts, and as more spectroscopic data becomes available, some of the most extreme high redshift candidates might turn out to be closer and less problematic for the standard model. Another issue is the estimation of stellar mass. Converting the observed brightness of a galaxy into an estimate of its stellar mass requires assumptions about the stellar population, including the ages of the stars, their metallicity, and the initial mass function. If any of these assumptions are incorrect, the inferred masses could be significantly off. For example, if early galaxies contain an unusually large number of very massive, luminous stars, they might appear very bright, but have less total stellar mass than initially estimated. Alternatively, if the galaxies are experiencing intense bursts of star formation, the light might be dominated by young, hot stars, making the galaxy appear more massive than it actually is. Dust plays a complicating role as well. Dust absorbs and scatters light, particularly at shorter wavelengths, and can affect both the observed colors and the total luminosity of a galaxy. If early galaxies contain significant amounts of dust, they might appear redder and dimmer than they would otherwise, affecting redshift estimates and mass estimates. JWST's infrared capabilities help mitigate some of these effects, as infrared light can penetrate dust more easily, but modeling the exact amount and distribution of dust remains challenging. Systematic uncertainties in the instruments themselves are another consideration. JWST is a new and complex observatory, and understanding its calibration and performance is an ongoing process. Small errors in the calibration of filters, detectors, or data processing pipelines could introduce biases that affect the inferred properties of galaxies. The JWST team has worked meticulously to characterize and correct for these effects. But with such faint and distant objects, even small uncertainties can have significant impact. As the mission progresses and more data is collected, our understanding of these systematics will improve. There is also the possibility of selection effects. JWST is observing a relatively small number of fields, and it is possible that the early massive galaxies it has found are rare outliers rather than representative of the general population. If so, then the tension with the standard model might be less severe than it appears. However, as more fields are observed and more galaxies are discovered, the statistics will become clearer, and we will be able to assess whether the early massive galaxies are truly as common as initial observations suggest. Some researchers have also pointed out that the definition of mass in early galaxies might need refinement. Galaxies at high redshift are observed during brief, intense phases of star formation, and their appearance might not reflect their typical state. If we are catching them during exceptional bursts, the inferred masses might not be representative of their average over time. Moreover, the processes of galaxy assembly, including mergers and accretion, are stochastic and variable, and it is possible that some galaxies experience rapid early growth followed by slower evolution. Despite these alternative explanations, the growing body of observations from JWST makes it increasingly difficult to dismiss the early massive galaxies as mere artifacts or outliers. Multiple independent teams have identified similar trends, and spectroscopic confirmations are accumulating. While some individual cases might be explained by observational systematics, the overall pattern suggests a real challenge to the standard model. The scientific community is right to be cautious and to demand rigorous confirmation. But the evidence is building that something interesting and potentially revolutionary is happening. The broader implications for physics: if JWST's observations truly indicate that something is wrong with our understanding of the early universe, the implications extend far beyond cosmology. They touch on fundamental aspects of physics, including general relativity, quantum mechanics, thermodynamics, and the nature of time. Understanding what might be wrong, or what might be missing from our theories, requires considering how these different areas of physics interconnect. General relativity, Einstein's theory of gravity, is the foundation of modern cosmology. It describes how matter and energy curve space-time, and it predicts how the universe expands and evolves. The Big Bang model and the Lambda CDM cosmology are built on general relativity, and any modification to the early universe timeline might require modifications to the theory itself. This does not necessarily mean that general relativity is wrong. It has been tested extensively and has passed every test with flying colours, but it might be incomplete, especially at the extreme conditions of the very early universe or near singularities. Quantum mechanics also plays a crucial role in the early universe. At the tiniest scales and highest energies, quantum effects dominate, and the classical description of space-time provided by general relativity breaks down. A complete theory of quantum gravity, which would unify general relativity and quantum mechanics, is one of the holy grails of theoretical physics. If such a theory predicts new phenomena in the early universe, such as a bouncing cosmology or a pre-Big Bang phase, it might resolve the tensions raised by JWST's observations. Several approaches to quantum gravity, including string theory, loop quantum gravity, and asymptotic safety, offer possible frameworks, though none has been definitively confirmed. Thermodynamics and statistical mechanics are also relevant. The second law of thermodynamics states that entropy or disorder always increases, and this law has profound implications for the arrow of time and the evolution of the universe. If the universe undergoes cycles, as some models propose, the accumulation of entropy becomes an issue. Each cycle should end with higher entropy than the previous one, and eventually the universe would reach maximum entropy and no further cycles could occur. Some cyclic models propose mechanisms to reset entropy during the bounce, but these mechanisms are speculative and not well understood. The nature of time itself might need to be reconsidered. In general relativity, time is a dimension of space-time, inextricably linked with space. The Big Bang represents a boundary of space-time where time begins. But some theories suggest that time might have existed before the Big Bang, either as a different kind of time or as part of a more fundamental structure from which space-time emerges. If time is an emergent phenomenon, arising from more fundamental quantum or informational principles, then the concept of before the Big Bang might be meaningful in ways that current theories do not capture. The implications also extend to the philosophy of science and the nature of scientific explanation. If we conclude that the Big Bang was not the absolute beginning, it raises the question of what preceded it and whether we can ever know. There might be fundamental limits to what we can observe or measure, not just due to technological constraints, but due to the nature of causality and the structure of space-time. This touches on deep philosophical issues about the scope and limits of human knowledge. Moreover, if the laws of physics were different in a pre-Big Bang phase, it raises questions about the constancy and universality of physical laws. Are the laws of physics eternal and unchanging, or are they contingent, emerging from more fundamental principles that might vary from one cosmic phase to another? These questions have been debated by philosophers and scientists for centuries, but the JWST observations are giving them a new urgency and a new empirical context. The future of JWST and next-generation observatories, JWST's mission is still in its early stages, and the telescope is expected to operate for many years to come, barring any unforeseen technical issues. As more data is collected, our understanding of the early universe will continue to evolve, and the mystery of the early massive galaxies will hopefully become clearer. But JWST is not the only telescope that will contribute to this effort. A new generation of observatories, both on the ground and in space, is being planned and built, and these instruments will provide complementary data that will help test and refine our theories. One of the most anticipated ground-based projects is the Extremely Large Telescope, or ELT, being constructed in Chile. With a primary mirror 39 meters in diameter, the ELT will be the largest optical and infrared telescope ever built. It will have the resolution to study individual stars and star clusters in distant galaxies, providing insights into the stellar populations and star formation histories of early galaxies. The ELT will also be able to measure the velocities and dispersions of stars and gas in these galaxies, helping to determine their masses and dynamics more accurately. Another major ground-based facility is the 30-meter telescope, or TMT, which is planned for construction in Hawaii. Like the ELT, the TMT will have a very large mirror and will be optimized for high-resolution observations at optical and infrared wavelengths. Together, these giant telescopes will complement JWST by providing detailed follow-up observations of the galaxies that JWST discovers. They will also be able to observe a broader range of wavelengths, including the optical range, where certain spectral lines are found, providing additional information about the chemical composition and physical conditions in early galaxies. In space, several new observatories are in various stages of planning. The Nancy Grace Roman Space Telescope, formerly known as JWST, is scheduled to launch in the mid-2022. Roman will have a field of view much larger than JWST's, allowing it to survey large areas of the sky and discover many more high redshift galaxies. Its capabilities in infrared imaging and spectroscopy will complement JWST, and together they will provide a more complete census of early galaxies and their properties. Further into the future, concepts for even more ambitious space telescopes are being discussed. The Habitable Exoplanet Observatory, or HabEx, and the Large UV, divided by optical, divided by infrared surveyor, or LUVOIR, are mission concepts that could provide unprecedented sensitivity and resolution, potentially allowing direct imaging of Earth-like exoplanets and detailed studies of the earliest galaxies. These missions are still in the planning stages, and their timelines and designs are subject to change, but they represent the next frontier in space-based astronomy. Gravitational wave observatories are also entering the picture. The Laser Interferometer Space Antenna, or LISA, is a space-based gravitational wave detector that will be sensitive to lower frequency waves than ground-based detectors like LIGO. LISA could detect gravitational waves from supermassive black hole mergers in the early universe, providing information about the growth of black holes and their role in galaxy formation. Combining gravitational wave observations with electromagnetic observations from telescopes like JWST will create a new era of multi-messenger astronomy. Advances in computational cosmology will also play a critical role. Modern supercomputers are capable of running ever more detailed simulations of the universe's evolution, modeling the interplay of dark matter, ordinary matter, star formation, black hole growth, and feedback processes. These simulations can be directly compared to JWST's observations, and discrepancies between the two can highlight where our models need improvement. As computing power continues to grow, and as our understanding of the relevant physics improves, simulations will become increasingly accurate and predictive. Artificial intelligence and machine learning are also being applied to the analysis of astronomical data. Algorithms can sift through vast datasets, identifying patterns and anomalies that might be missed by human researchers. Machine learning can also help refine models by finding optimal parameter values that match observations. As the volume of data from JWST and other telescopes grows, these computational tools will become indispensable. The human quest for knowledge. As we reflect on the discoveries being made by JWST and the questions they raise, it is worth stepping back to consider the broader human quest for knowledge and understanding. For as long as humans have existed, we have looked up at the sky and wondered. We have told stories about the stars, built monuments aligned with celestial events, and developed increasingly sophisticated tools to study the heavens. The question of where we come from, how the universe began, and what lies beyond the visible horizon are among the most profound questions we can ask. The scientific method, developed over centuries, has proven to be an extraordinarily powerful tool for answering these questions. By making observations, forming hypotheses, testing predictions, and revising theories in light of new evidence, science has uncovered truths about the universe that would have seemed like magic to our ancestors. We now know that the Earth orbits the Sun, that the Sun is one star among hundreds of billions in our galaxy, that our galaxy is one among hundreds of billions in the observable universe, and that the universe itself has a history, beginning with the Big Bang 13.8 billion years ago. Yet with each answer, new questions arise. The discovery of the expanding universe led to the question of what caused the expansion. The observation of galaxy rotation curves led to the discovery of dark matter. The measurement of distant supernovae led to the discovery of dark energy. And now, JWST's observations of early massive galaxies are leading us to question whether the Big Bang was truly the beginning. This iterative process, where each discovery opens new avenues of inquiry, is the essence of science. The questions JWST is raising are not just technical puzzles for specialists. They are questions about the nature of reality, the origin of existence, and the limits of human knowledge. They connect to deep philosophical and even spiritual traditions that have grappled with these issues for millennia. In asking whether anything can exist before the Big Bang, we are echoing ancient questions about creation, time, and the nature of being. Science does not replace these traditions, but it provides a new language and new methods for engaging with them. There is also something profoundly moving about the human capacity to ask and explore these questions. We are, as far as we know, the only species in the universe that has developed the ability to study the cosmos systematically and to ponder our place within it. This capacity is a product of billions of years of cosmic evolution, from the formation of the first atoms in the Big Bang, to the forging of heavy elements in stars, to the emergence of life on Earth, to the evolution of intelligence and consciousness. In some sense, we are the universe becoming aware of itself, asking questions about its own origin and destiny. The discoveries made by JWST and the debates they are sparking remind us that our knowledge is always provisional and subject to revision. No matter how confident we are in our theories, nature always has the capacity to surprise us. This humility in the face of the unknown is a core virtue of science, and it is what drives the relentless pursuit of new observations, better theories, and deeper understanding. The fact that we do not yet know whether anything exists older than the Big Bang is not a failure. It is an opportunity, a challenge, and an invitation to keep exploring. What this means for our cosmic perspective, the possibility that JWST has detected something older than the Big Bang, or at least structures that challenge our timeline of cosmic history, has profound implications for how we think about our place in the universe. If the Big Bang was not the absolute beginning, if time and space existed before it, or if our universe is part of a larger multiverse or a cyclical process, then our perspective on existence shifts in fundamental ways. One implication is that the universe might be far older, larger, and more complex than we ever imagined. Instead of a single timeline stretching back 13.8 billion years to a singular beginning, there might be layers of history, cycles of existence, or a vast multiverse of which our observable universe is just a tiny part. This is both humbling and awe-inspiring. It means that the cosmic story is even richer and more intricate than we thought, with chapters we have not yet read and perhaps cannot access directly. Another implication is that the conditions that gave rise to our universe, including the physical constants that allow for stars, planets, and life, might not be unique. If there are other universes with different properties, or if our universe is one phase in a series of cycles, then the question of why our universe has the properties it does becomes even more pressing. The anthropic principle, which suggests that we observe a life-friendly universe because we could not exist in any other kind, gains new significance if there are indeed many universes or many cycles with varying conditions. The idea that something might predate the Big Bang also has implications for how we think about causality and explanation. In science, we usually explain phenomena by tracing them back to prior causes. But if we reach a boundary, such as the Big Bang, where the laws of physics break down, or where time itself begins, then the chain of causality seems to terminate. If, however, there is something before the Big Bang, then the chain can continue, and we can ask what caused that prior state, and what caused the state before that, and so on. This raises the question of whether there is an ultimate beginning or whether the chain of causes extends infinitely into the past. These questions touch on deep issues in metaphysics and theology. Many religious and philosophical traditions have grappled with the concept of an eternal, uncaused first cause, often identified with God or the Absolute. If science finds evidence of a pre-Big Bang phase or of an eternal cyclic cosmos, it does not necessarily answer these metaphysical questions, but it provides new context for them. Some might see the possibility of an eternal or cyclic universe as supporting the idea of a self-sustaining cosmos that does not require a creator. Others might see the complexity and order of such a cosmos as evidence of design or purpose. For those who see the universe as purely physical, with no transcendent purpose or meaning, the idea of a vastly larger or older cosmos does not change the fundamental existential situation. We are still finite beings, living brief lives in an immense and ancient universe, and it is up to us to create meaning through our actions, relationships, and contributions. For those who see the universe as imbued with meaning, perhaps through the presence of a divine creator, or through some inherent teleology, the expanding scope of cosmic history might deepen the sense of mystery and wonder. Regardless of one's philosophical or religious perspective, the scientific exploration of these questions enriches our understanding and challenges us to think more deeply about who we are and why we are here. The discovery that there might be structures older than the Big Bang, if confirmed, would be one of the most significant revelations in the history of science, comparable to the Copernican revolution, the discovery of evolution, or the development of quantum mechanics. It would reshape our cosmic narrative and our sense of our place within it. The current state of the debate, so, has JWST truly detected something older than the Big Bang? The honest answer is that we do not yet know. The observations of early massive galaxies are real and well documented, but their interpretation is still subject to debate. There are alternative explanations that do not require radical revisions to cosmology, and more data is needed to rule these out definitively. However, the possibility that we are seeing evidence of a pre-Big Bang phase, or that the standard cosmological timeline needs significant revision, is being taken seriously by the scientific community. What we do know is that JWST has opened a new window on the early universe, revealing galaxies and structures that challenge our expectations and force us to reconsider our models. Whether the ultimate explanation involves new physics, modifications to the standard model, or a better understanding of star formation and galaxy assembly, the process of investigation is pushing the boundaries of human knowledge. The questions being raised are among the most profound we can ask, touching on the origin of the universe, the nature of time, and the limits of what we can know. The journey of discovery is far from over. JWST will continue to observe the early universe, collecting more data and refining our understanding. Other telescopes, both current and future, will contribute complementary observations. Theorists will develop new models and test them against the data. Computer simulations will become more detailed and realistic. And gradually, piece by piece, the picture will come into focus. We may find that the early massive galaxies can be explained within the standard framework after all, with some tweaks and refinements. Or we may find that a revolution in cosmology is needed, one that changes our understanding of the beginning and the history of the universe. Whatever the outcome, the exploration itself is valuable. It deepens our understanding, challenges our assumptions, and reminds us of the vastness and mystery of the cosmos. It connects us to a long tradition of thinkers and explorers who have asked similar questions and sought similar answers, and it reflects the best of human curiosity, ingenuity, and perseverance. The question of whether anything can be older than the Big Bang is not just a scientific puzzle. It is a window into the ultimate questions about existence, and pursuing it is one of the most meaningful endeavors we can undertake. Thank you for joining me on this exploration of one of the most exciting and puzzling discoveries in modern cosmology. If you enjoyed this deep dive, make sure to like this video, subscribe to the channel, and hit the notification bell so you never miss future content. Drop a comment below with your thoughts. Do you think JWST has really found something older than the Big Bang? Or do you think there's another explanation? And if you want to support the channel and help us create more in-depth explorations of the cosmos, consider becoming a patron or checking out our merchandise. Until next time, keep looking up, keep asking questions, and never stop wondering about the mysteries of the universe. The cosmos is vast, ancient, and full of secrets, and every new discovery brings us one step closer to understanding it all. The detailed timeline of early galaxy formation. To fully appreciate why JWST's discoveries are so surprising, we need to understand the standard timeline of early galaxy formation in much greater detail. According to the Lambda CDM model, the process begins with the quantum fluctuations generated during cosmic inflation. These tiny variations in density, stretched to cosmic scales by inflation, become the seeds from which all structure grows. At recombination, 380,000 years after the Big Bang, these fluctuations are imprinted in the cosmic microwave background as temperature variations of about 1 part in 100,000. After recombination, gravity begins to amplify these density differences. Regions that are slightly denser have slightly stronger gravity, attracting more matter and becoming denser still. This process is exponential, with small differences growing into large ones over time. However, the process is slow at first because the expansion of the universe works against gravitational collapse, and because ordinary matter and radiation are still partially coupled, with photons exerting pressure that resists compression. Dark matter plays a crucial role in speeding up this process. Because dark matter does not interact with radiation, it can begin clumping earlier and more efficiently than ordinary matter. By the time ordinary matter decouples from radiation at recombination, dark matter has already begun forming structures on various scales. These dark matter halos provide the gravitational wells into which ordinary matter can fall. Computer simulations show that the first dark matter halos, with masses around 1 million times the Sun, form within a few tens of millions of years after the Big Bang. These halos are the sites where the first stars will eventually form. The formation of the first stars, around 100 to 200 million years after the Big Bang, marks a crucial transition. These population 3 stars are massive, short-lived, and incredibly luminous. They begin to heat and ionize the surrounding gas, creating bubbles of ionized hydrogen. Their supernovae explosions distribute the first heavy elements, carbon, oxygen, silicon, iron, into the surrounding medium, enriching the gas from which subsequent stars will form. The presence of these heavy elements changes the cooling properties of the gas, making it easier for gas to collapse and form stars. This feedback loop accelerates structure formation. The first proto-galaxies are thought to form from the merger of several dark matter halos, each containing stars and gas. These early galaxies are small, with masses of only a few 100 million solar masses, and they are irregular in shape, without the organized structures of spiral arms or elliptical profiles that characterize more mature galaxies. Star formation in these early systems is intense but intermittent, driven by episodes of gas infall and regulated by feedback from supernovae and stellar winds. As time progresses, these proto-galaxies continue to merge and grow. The hierarchical assembly process means that larger structures form from the merging of smaller ones. By about 500 million years after the Big Bang, galaxies with masses of several billion solar masses should begin to appear, though they would still be smaller and less organized than galaxies in the nearby universe. Spiral galaxies, with their characteristic disk structures and spiral arms, are not expected to form until later, around 1 to 2 billion years after the Big Bang, when there has been enough time for gas to settle into rotating disks and for gravitational interactions to shape the spiral patterns. This standard timeline is based on a combination of theoretical modeling, computer simulations, and observations from telescopes like Hubble. Hubble has observed galaxies at redshifts up to about 11, corresponding to times around 400 million years after the Big Bang. And these galaxies largely conform to expectations. They are small, actively star-forming, and relatively metal-poor. JWST, with its superior sensitivity, was expected to push this boundary back, finding even earlier galaxies that would be even smaller and more primitive. The surprise is that many of the galaxies JWST is finding at high redshifts do not fit this pattern. They are larger, more massive, and more evolved than they should be at such early times. The tension can be quantified by comparing the observed stellar masses of high redshift galaxies to the predictions of simulations. State-of-the-art simulations, which incorporate the best current understanding of dark matter, star formation, and feedback, predict that galaxies with stellar masses above 10 billion solar masses should be extremely rare at redshifts above 10. Yet JWST has found multiple candidates with such masses at these redshifts, and some even higher. The observed number density of massive galaxies is orders of magnitude higher than predicted, suggesting that either the simulations are missing something important or the observational interpretations need revision. One key question is how efficiently gas is converted into stars in these early galaxies. The star formation efficiency is the fraction of gas that turns into stars, rather than remaining as gas or being expelled from the galaxy by feedback. In nearby galaxies, this efficiency is typically a few percent. If the efficiency were much higher in the early universe, perhaps 10 or 20%, it could help explain the rapid buildup of stellar mass. However, increasing the efficiency has other consequences, such as altering the amount of gas available for later star formation and affecting the metallicity evolution of galaxies. These consequences need to be checked against observations. Another factor is the initial mass function, the distribution of stellar masses at birth. In nearby galaxies, the IMF is such that most stars are low mass and only a small fraction are high mass. If the IMF in the early universe were different, with more high-mass stars, then the light per unit stellar mass would be higher, and galaxies might appear brighter without being as massive. However, high-mass stars also produce more supernovae and more feedback, which could suppress further star formation, so the net effect is not straightforward. The role of mergers is also important. In a hierarchical universe, galaxies grow not only by accreting gas and forming stars, but also by merging with other galaxies. Major mergers, where two galaxies of comparable mass collide, can trigger intense bursts of star formation and rapidly increase the total stellar mass. If mergers were more frequent in the early universe than simulations predict, it could accelerate galaxy growth. Observations from JWST are beginning to reveal the merger rates at high redshifts, and early indications are that mergers might indeed be more common than expected. The mystery of supermassive black holes. One of the most puzzling aspects of JWST's observations is the presence of supermassive black holes in some of the earliest galaxies. Supermassive black holes, with masses ranging from millions to billions of times the Sun, are found at the centers of most large galaxies today, including our own Milky Way. The relationship between the mass of a galaxy's central black hole and the mass of its stellar bulge is well established, suggesting a deep connection between black hole growth and galaxy evolution. However, the origins of these supermassive black holes remain one of the great unsolved problems in astrophysics. In the standard picture, supermassive black holes grow from much smaller seed black holes, formed by the collapse of the first massive stars, or from the direct collapse of gas clouds in dense environments. These seed black holes then grow over billions of years by accreting gas from their surroundings and by merging with other black holes when galaxies collide. The growth rate is limited by the Eddington limit, which is the maximum rate at which a black hole can accrete matter before the radiation pressure from the infalling material pushes the gas away. Even at the Eddington limit, growing a black hole from a stellar mass seed of a few tens of solar masses to a billion solar masses takes about 1 billion years. JWST has detected active galactic nuclei, the bright emission from gas spiraling into supermassive black holes in galaxies at redshifts above 10 when the universe was less than 500 million years old. Some of these black holes appear to have masses in the millions or even tens of millions of solar masses. If they grew from stellar mass seeds through standard accretion, there simply has not been enough time for them to reach such large masses. This suggests that either the seed black holes were much more massive than previously thought, or that the growth rate was somehow faster than the Eddington limit, or that the black holes formed through a different mechanism entirely. One possibility is that the seed black holes were formed through the direct collapse of massive gas clouds in the early universe, creating black holes with masses of thousands or even hundreds of thousands of solar masses right from the start. This could happen if the gas clouds were able to collapse without fragmenting into stars, which requires special conditions such as low metallicity and the absence of certain cooling mechanisms. These direct collapse black holes would provide a much larger starting point for growth, making it easier to reach supermassive scales in the time available. Another possibility is that black holes in the early universe were able to accrete at super Eddington rates, perhaps because the surrounding gas was denser, or because magnetic fields and other effects reduced the radiation pressure. Some theoretical models suggest that black holes in rapidly rotating or highly magnetized environments might be able to grow faster than the Eddington limit by channeling the radiation away in jets rather than spherically. If this process was common in the early universe, it could explain the rapid growth of supermassive black holes. Primordial black holes, formed in the first moments after the Big Bang from density fluctuations or phase transitions, offer yet another possibility. If primordial black holes with intermediate masses, say thousands to millions of solar masses, exist, they could serve as seeds for supermassive black holes without requiring any stellar progenitors. As discussed earlier, constraints from various observations limit the abundance of primordial black holes, but there are still parameter ranges where they could exist and contribute to the observed supermassive black hole population. The presence of supermassive black holes in early galaxies has implications beyond just the black hole formation problem. Black holes can influence galaxy evolution through feedback. As gas falls into a black hole, it heats up and emits radiation, and in some cases, the black hole drives powerful jets and winds that can expel gas from the galaxy or heat it to high temperatures. This AGN feedback can suppress star formation, limiting how large a galaxy can grow. In the early universe, if AGN feedback were particularly strong, it could help explain why some galaxies stopped forming stars, and why the stellar mass function has the shape it does. However, the timing and efficiency of AGN feedback in the early universe are uncertain. JWST's observations of high redshift AGN are providing new data on the frequency and luminosity of these objects, and on the properties of the gas around them. By studying the spectra of early AGN, astronomers can measure the velocities of outflowing gas, the ionization state of the gas, and the energy being injected into the surrounding medium. This information is crucial for understanding how black holes and galaxies co-evolve, and for building more accurate models of galaxy formation. Chemical enrichment and metallicity. Another important clue about the early universe comes from measurements of metallicity, the abundance of elements heavier than hydrogen and helium. In astronomy, these heavier elements are called metals, and they are produced in the cores of stars and distributed into space by supernova explosions and stellar winds. The first stars, which formed from primordial gas containing only hydrogen and helium, had zero metallicity. As these stars lived and died, they enriched the surrounding gas with metals, and subsequent generations of stars were born with higher metallicities. Metallicity is important for several reasons. It affects the cooling properties of gas, which in turn affects how efficiently gas can collapse to form stars. Higher metallicity gas can cool more efficiently because metal atoms and ions radiate energy effectively, allowing clouds to collapse to higher densities and form lower mass stars. Metallicity also affects the lifetimes and fates of stars, with metal-rich stars evolving differently from metal-poor stars. And metallicity provides a kind of clock tracing the history of star formation and chemical enrichment in a galaxy. JWST is capable of measuring the metallicity of early galaxies by analyzing the emission lines in their spectra. Certain spectral lines, such as those from oxygen, nitrogen, and carbon, are produced by gas that has been ionized by young stars, and the ratios of these lines can be used to infer the metallicity. Early results from JWST show that some high redshift galaxies have surprisingly high metallicities for their ages, comparable to galaxies in the nearby universe. This suggests that they have already undergone significant star formation and chemical enrichment, building up metals rapidly. Rapid metal enrichment could occur if star formation were very efficient, converting a large fraction of gas into stars in a short time, or if the initial mass function was skewed toward massive stars, which produce more metals per generation. Alternatively, it could indicate that the galaxies have experienced multiple episodes of star formation, with early generations of stars already having enriched the gas by the time JWST observes them. Understanding the metallicity evolution of early galaxies is crucial for reconstructing their star formation histories and for testing models of chemical enrichment. There is also the question of how metals are distributed within and between galaxies. In the early universe, supernovae and stellar winds could eject metal-enriched gas from small galaxies, distributing it into the intergalactic medium. This enriched gas could then be accreted by other galaxies, spreading metals across the cosmos. Observations suggest that even the intergalactic medium at high redshift contains trace amounts of metals, indicating that some enrichment has already occurred. Understanding this process of galactic outflows and inflows is important for understanding the overall chemical evolution of the universe. JWST's spectroscopic capabilities are particularly valuable for studying metallicity. Unlike photometric observations, which measure the total light in broad wavelength bands, spectroscopy breaks the light into its component wavelengths, revealing the detailed absorption and emission features that correspond to different elements and ions. By measuring these features in high redshift galaxies, astronomers can determine not only the overall metallicity, but also the relative abundances of different elements, such as the ratio of oxygen to iron or nitrogen to oxygen. These abundance ratios provide additional constraints on the types of stars that produce the metals and the timescales of enrichment. Some early JWST results have shown galaxies with unusual abundance patterns, different from what is seen in nearby galaxies. For example, some galaxies show elevated nitrogen to oxygen ratios, which could indicate the presence of massive stars or special stellar populations. Others show evidence of rapid oxygen enrichment, suggesting that massive stars and supernovae dominated the early enrichment process. These observations are prompting theorists to refine their models of stellar nucleosynthesis and chemical evolution, and they are providing new tests of how stars form and evolve in extreme environments. The first billion years in detail. Let's walk through the first billion years after the Big Bang in even greater detail, highlighting the key milestones and transitions that shape the early universe. This timeline, based on the lambda CDM model and constrained by observations, provides the backdrop against which JWST's surprising findings must be understood. At time zero, the Big Bang occurs. The universe is unimaginably hot and dense, with temperatures far exceeding billions of degrees. In the first fraction of a second, cosmic inflation stretches quantum fluctuations to cosmic scales, setting the stage for all future structure. After inflation ends, the universe is filled with a hot plasma of particles, including quarks, gluons, electrons, neutrinos, and photons. As the universe expands and cools, quarks combine to form protons and neutrons, the building blocks of atomic nuclei. By about 1 second after the Big Bang, the temperature has dropped to about 10 billion degrees, cool enough for protons and neutrons to stick together. Over the next few minutes, nuclear reactions produce helium-4, deuterium, helium-3, and lithium-7 specific ratios. About 75% of the ordinary matter remains as hydrogen, and about 25% becomes helium. These primordial abundances are a key prediction of Big Bang nucleosynthesis and have been confirmed by observations. For the next 380,000 years, the universe continues to expand and cool, but it remains opaque. Electrons and photons are tightly coupled, and light cannot travel freely. As the temperature drops below about 3000 Kelvin, electrons and protons combine to form neutral hydrogen atoms, and the universe becomes transparent. This is recombination, and it releases the cosmic microwave background radiation. From this point on, the CMB photons stream through space, cooling and redshifting as the universe expands. After recombination comes the cosmic dark ages, a period when the universe is filled with neutral hydrogen, but no stars have yet formed. The universe is dark, illuminated only by the fading glow of the CMB. During this time, gravity is slowly pulling matter together, amplifying the density fluctuations imprinted during inflation. Dark matter clumps into halos, and ordinary matter begins to accumulate in the centers of these halos. Around 100 to 200 million years after the Big Bang, the first stars ignite. These population 3 stars are massive and luminous, burning brightly for only a few million years before exploding as supernovae. Their ultraviolet light begins to ionize the surrounding hydrogen, creating bubbles of ionized gas. The first galaxies, small and irregular, assemble from the mergers of dark matter halos containing these early stars. Star formation is intense but episodic, driven by gas infall and regulated by supernova feedback. By about 400 million years after the Big Bang, corresponding to a redshift around 10 to 11, small galaxies are beginning to merge and grow. The ionized bubbles around individual galaxies begin to overlap, and the epoch of reionization is underway. Observations from Hubble have revealed galaxies at this epoch, and they appear as expected, small, actively star-forming, and with low metallicities. JWST, observing at this same epoch, is finding some galaxies that match these expectations, but also many that do not. By 500 to 600 million years after the Big Bang, reionization is well advanced, and a significant fraction of the universe is ionized. Galaxies are growing through continued star formation and mergers. The first supermassive black holes are beginning to form, though their origins remain mysterious. The cosmic web is becoming more defined, with galaxies clustering along filaments and accumulating in nodes. By about 1 billion years after the Big Bang, corresponding to a redshift around 6, reionization is complete. The universe is fully ionized and transparent to ultraviolet light. Galaxies have grown to masses of tens of billions of solar masses, and the first large-scale structures, protoclusters of galaxies, are beginning to form. This marks the end of the early universe and the transition to the era of galaxy maturation. Throughout this first billion years, the rate of structure formation is governed by the interplay of gravity, expansion, cooling, star formation, and feedback. The Standard Model makes specific predictions about how this process unfolds, and these predictions have been tested against observations from Hubble and other telescopes. JWST's observations are now testing these predictions at even earlier times and with greater precision, and the results are challenging some of the assumptions underlying the standard timeline. The broader context of cosmological tensions, the issues raised by JWST's observations, are not occurring in isolation. Over the past decade, several tensions and anomalies in cosmological data have emerged, each calling into question different aspects of the standard lambda CDM model. While no single issue is definitive on its own, together they suggest that our understanding of the universe might be incomplete. Understanding these broader tensions provides important context for interpreting JWST's findings. The Hubble tension, which we discussed earlier, is perhaps the most prominent. Measurements of the current expansion rate from the cosmic microwave background and from local distance indicators disagree by about 9%, a statistically significant discrepancy. If the local measurement is correct, the universe is expanding faster than the CMB predicts, which has implications for the age of the universe, the timeline of structure formation, and the properties of dark energy. Resolving this tension might require new physics, such as early dark energy, additional relativistic particles, or modifications to gravity. Another tension involves the clustering of matter on large scales, quantified by a parameter called sigma-8. Measurements of sigma-8 from the cosmic microwave background and from galaxy clustering and weak gravitational lensing show some disagreement, with lensing measurements tending to give lower values. This could indicate that the universe is less clumpy on large scales than the CMB predicts, which might suggest that dark matter has different properties than assumed, or that gravity behaves differently on large scales. There is also the lithium problem. Big Bang nucleosynthesis predicts the primordial abundance of lithium-7, but observations of old stars in our galaxy show lithium abundances that are a factor of 3 lower than predicted. This discrepancy has persisted for decades and remains unexplained. It could indicate that our understanding of stellar physics is incomplete, or it could suggest that something about the conditions in the early universe was different from what we assume. The so-called axis of evil is an anomaly in the cosmic microwave background. Certain large-scale patterns in the CMB, particularly the quadrupole and octupole moments, appear to be aligned with each other and with the plane of the solar system, which seems highly unlikely to occur by chance. Some researchers suggest that this alignment is a statistical fluke, while others propose that it might indicate violations of the cosmological principle or the presence of large-scale structure beyond the observable universe. The cold spot in the CMB is another anomaly. This is an unusually large cold region in the CMB, much larger and colder than would be expected from random fluctuations. Various explanations have been proposed, including the presence of a supervoid, a large region of space with lower than average density, or more exotic ideas like the signature of a collision with another bubble universe. No consensus has been reached, and the cold spot remains an open puzzle. These tensions and anomalies, individually, might be explainable through systematics, statistical flukes, or refinements to the standard model. But collectively, they suggest that there might be something we are missing. JWST's observations of early massive galaxies add another data point to this list, and they raise the possibility that the standard model, while remarkably successful in many respects, might need significant revision or extension. Whether the resolution comes from better measurements, better models, or genuinely new physics remains to be seen. The path forward, as the cosmology community grapples with JWST's observations and the questions they raise, what is the path forward? How can we determine whether the early massive galaxies truly indicate a problem with the standard model, or whether they can be explained within the existing framework? The answer lies in a combination of more observations, better models, and rigorous testing of alternative hypotheses. First, more spectroscopic observations are essential. Photometric redshifts, while useful for identifying candidates, are not sufficiently reliable for definitive conclusions. Spectroscopy provides much more accurate redshifts and also reveals detailed information about the stellar populations, metallicities, star formation rates, and ionization states of galaxies. JWST's NIRSpec instrument is being used extensively for this purpose, and large spectroscopic surveys are underway to confirm and characterize high redshift galaxies. Second, multi-wavelength observations are crucial. Combining data from JWST's infrared observations with observations at other wavelengths, such as radio, submillimeter, and X-ray, provides a more complete picture of galaxy properties. Radio observations can trace the cold gas and dust in galaxies. Submillimeter observations can detect heavily obscured star formation, and X-ray observations can identify active galactic nuclei and reveal hot gas in galaxy halos. By combining all these observations, astronomers can build comprehensive models of early galaxies and test their predictions against the data. Third, improved simulations are necessary. Current simulations of galaxy formation are sophisticated, but they still rely on approximations and subgrid models for processes that occur on scales too small to be resolved directly. Processes like star formation, feedback from supernovae and AGN, and the interaction between gas and dark matter are complex and uncertain. Next-generation simulations, running on more powerful supercomputers and incorporating more detailed physics, will be able to make more accurate predictions. Comparing these predictions to JWST's observations will help identify which aspects of the models need revision. Fourth, alternative cosmological models need to be explored systematically. If the standard lambda CDM model cannot accommodate the observations, even with reasonable modifications to astrophysical processes, then we need to consider more radical alternatives. This includes models with modified gravity, different dark matter properties, varying fundamental constants, or pre-Big Bang phases. Each of these alternatives makes specific predictions that can be tested against observations, not just from JWST, but from the cosmic microwave background, large-scale structure surveys, gravitational wave detectors, and other sources. Fifth, interdisciplinary collaboration is essential. The questions raised by JWST's observations touch on many areas of physics and astronomy, from cosmology and astrophysics to particle physics and quantum gravity. Solving these puzzles will require input from theorists and observers, from specialists in galaxy evolution, CMB physics, computational cosmology, and fundamental physics. Conferences, workshops, and collaborative projects bring together researchers from different fields to share ideas and develop new approaches. Sixth, public engagement and education are important. The discoveries being made by JWST are not just of interest to specialists. They capture the imagination of the public and inspire the next generation of scientists. Communicating these discoveries clearly and accurately, while also conveying the uncertainties and the process of scientific inquiry, helps build public support for science and fosters a culture of curiosity and critical thinking. The meaning of cosmic discovery, the possibility that JWST has detected something older than the Big Bang, or at least structures that challenge our understanding of cosmic history, is a reminder of the dynamic and evolving nature of science. Our current theories, no matter how successful, are always provisional and subject to revision in light of new evidence. The willingness to question assumptions, to test predictions rigorously, and to revise theories when necessary is what makes science such a powerful tool for understanding the universe. The questions JWST is raising are among the most profound we can ask. They touch on the origin of the universe, the nature of time, the limits of human knowledge, and our place in the cosmos. These are not just technical questions for specialists, but questions that resonate with deep philosophical and existential themes. In exploring them, we are continuing a quest that has occupied thinkers for millennia, a quest to understand where we come from, how the universe began, and what lies beyond the boundaries of the known. Whether the ultimate answer involves new physics, a revision of the standard model, or a better understanding of astrophysical processes, the journey of discovery is valuable in itself. It pushes the boundaries of human knowledge, reveals the beauty and complexity of nature, and reminds us of the vastness and mystery of the cosmos. Every new observation, every refined measurement, every theoretical insight brings us closer to understanding the universe and our place within it. As we continue to observe the universe with JWST and other telescopes, as we build more sophisticated models and test them against data, as we explore alternative theories and push the limits of our understanding, we are engaged in one of humanity's most noble endeavors. The search for truth, the desire to know, and the courage to question are what define us as a species. And in asking whether anything can be older than the Big Bang, we are reaching toward the ultimate questions about existence itself. The cosmos is vast, ancient, and full of mysteries. Every answer we find raises new questions, and the process of inquiry is never-ending. But that is what makes the journey so exciting and so meaningful. We may never know all the answers, but the act of asking, exploring, and discovering is what enriches our lives and connects us to something greater than ourselves. The universe is calling, and with telescopes like JWST, we are answering that call, one discovery at a time.